All right, so in this section, we're going to be going into the concavity of a function. So we're going to be talking about like what the shape of a function, is in regards to like how it would be increasing or decreasing, and how that relates to the derivative and second derivative. So let's first go over just the formal definition of concavity, and then we'll go over like a picture of what this means, showing this. So let's say f is a differentiable function on an open interval I. Then we say the graph of the function f is concave upward when the first derivative is increasing. It's concave downward on the open interval I when the first derivative is decreasing. Now, don't confuse increasing with the derivative having to be positive, and don't confuse decreasing with it having to be negative. That's a common mistake. So let's look at this graph and get a good understanding of what it means to be concave up or concave down. So when we say concave down, we're talking about this first region, like this whole part right here, up to this point B. This part is concave down, all concave down. Concave down there. From here to here, it's concave down. And then concave down on this last part. Everything in pink is concave down. Now, let's focusing just on the concave down part. If we were to, let's analyze what the derivative is doing there. If we let's say we take the derivative like over here. Okay, let's draw a tangent line. I'll draw a tangent line here. Something like that. That's not very tangent line. I like that's the derivative tangent point. The slope of the tangent line here is positive. We can say f prime here is greater than 0. Now, later on the graph, let's see if we can grab a little ruler. Later on that same part, like up here, the tangent line is horizontal. That means f prime equals 0 there. And either like past that over here, f prime is negative. F prime is below 0. So see, the first derivative is positive, 0, and negative, all on that first pink region where it's concave down. So again, it's not necessarily the sign of the first derivative. What we're talking about is that, see, it's decreasing. It's going from a positive number all the way to a negative number. So the first derivative is decreasing there. Now, over here, same thing. We have, over here, we have, maybe the tangent line looks like that. But towards the end, it becomes more flat. So see, it goes from positive to maybe like being 0. So it's decreasing there too. And here as well. We drew a tangent line over here. And then over here, we drew a tangent line. See, it's going from slightly negative, kind of flat, very steep downward. Now, what does that mean in terms of, what's going on there? Well, if you think about it, remember, the derivative describes how the function is changing. So when the function is increasing, the first derivative is positive. But now let's think about if we want to understand how the first derivative is changing. So if we took the derivative of the derivative, we're talking about the second derivative. So here, where it's concave down, the first derivative is decreasing. So that means that the second derivative, or the derivative of the derivative, is negative. The second derivative here is less than 0, all on these pink region. Second derivative here is less than 0, on here and on here. because that's saying that the first derivative is decreasing. Remember, the second derivative is the derivative of the derivative. It's gonna be a little, kind of confusing to wrap your head around it at first, but after you practice with it, it's actually pretty simple. Now let's look at the other regions where it's concave up. So here it's concave up. I put that in pink or purple. Concave up here, concave up here, concave up there. So it's kind of the opposite of when it's concave down. When it's concave up, that means at those regions, the first derivative is increasing. See, because we drew a tangent line over here, first derivative over here, is negative. First derivative is less than 0 here. But over here, the first derivative is 0. It's horizontal about. And then even over here, it's positive. First derivative is above 0. So the first derivative is increasing whenever it's concave down. We can apply that, over on this part. It's negative here. First derivative is 0 there. And it's positive here. So it's going from negative to 0, positive. And again here, negative, less negative, that sort of thing. So when it's concave down, that means the first derivative is increasing. And again, thinking about the second derivative. If the first derivative is increasing, that means the second derivative is positive because the second derivative describes how the first derivative is changing. So that means whenever it's concave upward, the first derivative is positive. Positive here, positive here, and positive here. An easy way to conceptualize it is just think about, when you drive a car. Your speed is your velocity, what you see on the odometer, but your acceleration describes how your speed is changing. So when your acceleration is positive, that means you're increasing speed. When your acceleration is negative, it means you're slowing down. So think of the acceleration as the second derivative, and the first derivative is your velocity. So it's that sort of thing. So let's go look at this now, the formal definition of concavity here. So there's, what I basically just went over formally. So if we look at the second derivative and figure out the sign of it, when its second derivative is positive for all the values of x in the open interval, and it's concave up on that interval. If the second derivative is negative for all the values in that interval, and it's concave downward on that interval. So let's go through a practice problem so we can really apply this stuff and learn, what it means more deeply. Let's go through problem 18 here. Okay, so we want to figure out where the graph of the function is concave up or concave down. So what we're going to do is we want to essentially study the second derivative. So we're going to figure out what the second derivative is, find essentially the critical values or the zeros of the second derivative, and break our interval up at those values and see what's going on with the sign of the second derivative. So going through this. Use the product, reuse the quotient rule, we'll get that time of x. It'll be, the derivative bottom or bottom squared. Over the derivative of top times the bottom minus top times the derivative of the denominator. Now I'm gonna zoom ahead of this because this is not the important part. But, you should be competent in this, but make sure you check your work when you take this. So I'm gonna go ahead and zoom ahead and show you what this first derivative will end up being and what the second derivative equation will be. All right, so after take the second derivative and simplify, we'll get that it's equal to 36x squared minus 36 over x squared plus 3 to the third power. So we find now where this is equal to 0, or where it's undefined. So it's not going to be undefined anywhere because x squared plus 3 can never be negative. So we find the zeros of this. We find where f prime of x equals 0. We just set the numerator equal to 0. So 0 equals 36x squared minus 36. Get that. 0 equals, in fact, out 36. 36 times x squared minus 1. 36 times x minus 1. So we get points, we want to check to see what's going on when x is -1 and when x is +1. So we're going to break our intervals up at these points. So let's set up a table. I like to even set it up this way. Interval on top. We're going to go from -infinity to -1, -1 to 1, and 1 to infinity. That's some value. Those intervals. Figure out what's going on with the second derivative. And draw a little sketch of what the graph of f of x is doing. What its behavior is. All right, so let's set some easy value. Let's set -2, 0, and 2. So we're going to evaluate the second derivative at -2, 0, and 2. So f double prime of -2, f double prime of 0, and f double prime of 2. And we really only care about the signs. So f double prime of -2, we plug -2 into here. And again, make sure we divide by that. Well, this whole thing, I guess. So we're going to have 36 times -2 squared. So 36 times 4 minus 36 over -2 squared. So 4 plus 3. So over 7 cubed. And we're going to get a positive number here. Okay, 36. This is bigger than that. So again, we only care that it's positive. So we're going to have a positive value. So let's put positive here, like that. F double prime of 0. So we'll have 36 times 0 minus 36. And then we leave a little more space here. Six over 0 plus 3 cubed, so 3 cubed, 23, 9, 27. We're going to have -36 over 27. So see, we have a negative number. It's less than 0. So have a negative value there. And then we figure out what f double prime of 2 is. So 36 times 4 minus 36 over 4 plus 3 cubed, so it's going to be 7 cubed. So the same as what we got for f of -2, since they both become positive. And so we're going to have that this is a positive number greater than 0. So positive there. Positive, positive, negative. And so then, using what the theorem says about concavity, when the second derivative is positive, that means the graph is going to be concave up on this interval. Concave up there, concave up there. And since it's negative here, the graph is going to be concave downward. And we don't have any undefined values for this function. So then we don't have to worry about, figuring out there's like an asymptote or anything at -1, 1. So then we can just summarize, say that f of x is concave upward on -infinity to -1 and 1 to infinity. And it's concave downward on -1 to 1. There we go. That's all there is to it.